Hello, welcome to our webinar on Introduction to Science Research and Solving the Crisis in Cosmology, Determining the Evolution of the Hubble Parameter Across Time Using Linear Cosmography. I'm Yu Zhu, a rising senior from Great Neck South High School, New York State. I'm also the founder of the International Student Astronomy Organization. We are a global community of high school students passionate about exploring the universe, and our mission is to raise astronomy awareness and prepare middle and high school students worldwide by providing knowledge for astronomy research, opportunities, and global collaborations. I will be your moderator for this webinar. Our invited speaker today is Aidan Jing, a rising senior at Great Neck North High School. Hi, Aidan. Would you please introduce yourself?
Hi, so my name's Aidan. I'm a rising senior from New York, and my journey with astrophysics personally began when I watched the show Cosmos, as a toddler on Netflix, and I've been exploring my interest in this field through research in cosmology, and I've won awards for this research. And on the academic side, I've qualified as a physics Olympiad semifinalist, and I'm not only passionate about, exploring this field myself, but I want to bring the wonder of physics to others. So I run my school's physics and astronomy club. And what we do is we kind of organize stage demonstrations for elementary school students. And outside of STEM, I enjoy learning languages. I've spent a summer in Morocco learning Arabic as an exchange student, and I do debate competitively. And in my free time, I just like, chilling with my friends and playing Valor.
Thank you, Aidan. And today, Aidan will talk about Introduction to Science Research and Astronomy-related research. And this talk will basically trace his recent research projects on solving the crisis in cosmology, determining the evolution of Hubble parameter across time using linear cosmography. This event will be recorded and made available on YouTube for future reference. Aidan, would you please share your full screen?
Yes. Give me a second.
All right.
Oh, can you guys see everything fine? Wait. Okay. So, as Flora said, my project is about solving the crisis in cosmology. But first, I want to just talk about research in general and give some tips and advice. So, my first tip is that, you have to find something you're interested in, and this seems obvious, but I find that a lot of times people will go into fields they see as like prestigious or will win them like awards. They won't go into stuff they really like actually are passionate about. I'm not saying you have to be an expert or you don't have to like go to bed thinking about, your subject area, you don't have to love it that much, but if you aren't invested in your research, it's gonna kind of backfire because one, it's just gonna be painful to, slog through the research itself. And if you're not enthusiastic and you don't have some sort of like base knowledge of your field, it'll show to judges. Because especially at the high school level, they're not really evaluating just your research, but also your potential as a scientist. So that includes your knowledge of the field you're kind of doing. Um, After you have chosen a topic, I would recommend you read like past papers and familiarize yourself with the literature of the field. And this is crucial, again, one, when you're presenting to judges, because again, they're looking for expertise in the field. And two, if you're just cold emailing mentors, they get, hundreds of these applications from undergrads and high school students. They need a reason to take you, basically. So if you're not familiar with their work specifically and the general work in the field, they won't want to, take you under their wing. You have to prove yourself to them, basically, before you even start working with them. And finally, I would suggest try to be adaptable and try out new approaches. I know this is cliche, but science is about failure and learning from it. There's been so many times when my code has failed, like right now I'm working on debugging it because I tried to add this new data set and it didn't work out. The point of it is to find ways around it, and it's only through these issues that, you really learn stuff because if everything goes as planned, like what was the point of even doing the study, right? So and also, when you have these challenges, they provide again valuable experiences to learn from and discuss with, either judges or peers, and it's just a good experience. So don't be discouraged if everything doesn't go, smoothly. It's not supposed to just go smoothly. So without further ado, I'm going to start talking about my research specifically. Here we go. So what is the crisis in cosmology that I speak of? So there are two leading methods to measure something called the Hubble constant. So the Hubble constant, you can just think about as is the rate of expansion of the universe. So ever since the ever since the early 1900s when Edwin Hubble discovered the universe was expanding, we've had to quantify it using a value. So in modern cosmology we use the Hubble constant. It's in kilometers per second per megaparsec. So what the megaparsec is a measure of distance. So what this means is that for each megaparsec, this is how much faster, and kilometers per second is a measure of velocity or speed. So for each megaparsec, this is how fast stuff is moving away from us. um there are two main methods to measure this. One is standard candles. So what these are basically supernovae, which what is what I use, and these are late universe measurements. What I mean by this is that when you take the light data from this is happening like close because the universe is roughly like 14 billion years old right now. These measurements are from like only a few billion years ago. The other ways to use data from something called the CMB or cosmic microwave background. This is like a few 100,000 years after the Big Bang. So this is like 13 point something million years, a billion years ago. And essentially when you get the rate of expansion with these two different sets of data, you get two values that are in massive disagreement. So you can see like these numbers are kind of close, but look at the error bars, right? They're very small. So these are like five error bars away from each other. And the chance that they're actually like they agree with each other is like in the one in the millions. So this is called a tension in like cosmology when like two values are in like such big disagreement that like basically you almost know for certain that something's wrong with your like the way you're analyzing it, not the data itself. The other thing is that our current standard model of cosmology, it says that dark energy is something called the cosmological constant, and what it is it's this like background vacuum energy that rips stuff apart. Because when you think about the universe, right, and like gravity, you wouldn't expect the universe to expand. You'd expect it to like contract because gravity like mass pulls other mass together. So cosmologists they posited this thing called dark energy, and they said that the reason why the universe is accelerating now is why it's expanding is because dark energy, unlike mass, as the universe gets stretched out, it doesn't get weaker, it actually stays the same. And they said that this is why the universe is expanding because over time dark energy becomes more powerful than matter. But new studies in the field show that are hinting at least that dark energy is not the same over time and it actually might get stronger over time. So this is in again direct disagreement with what our current model predicts. So the data I used is from the Dark Energy Supernova program, and this is kind of an international collaboration to probe the nature of dark energy. And they came out with their 5-year data release in 2024, and this is massive because they quintupled the number of high quality. This is WISE measure of redshift supernovae. So what you should know about redshift is that the higher the redshift is, basically, the farther back in time you're looking. So a redshift of y equals 1 would correspond to the age of the Big Bang, while y equals 0 is like literally if the star exploded right now. And what's so important about these supernovae is that they're standard candles. So I mentioned what a standard candle was before, but now I'll like elaborate. So the problem with when you're trying to measure distances in not just cosmology but astronomy in general is that like take the sun, for example, right? The sun is obviously the most bright star in the sky, but compared to most stars in the universe, it's actually like a middle-sized star. The reason why it's so bright is it's close to us. The issue is that, again, when you look at stars in the sky, how bright they look to us is a function of both how bright they actually are, their luminosity, and how far they are. So we can't actually tell the distance because a star that looks dim might actually be really bright. It's just really far from us. So what we need is to eliminate one of these variables, right? You can't solve a three-variable equation with two unknowns. Type 1a supernovae are the special type of supernovae that occur in a binary star system where one of the stars is a white dwarf. And what's special about these is that these white dwarfs all explode when they hit a certain mass, and they all explode with the same luminosity or brightness. So if we identify these supernovae as type 1a supernovae, we know their luminosity. So that's not unknown anymore, and we can directly get their distance. And that's really important for cosmology. So that's why they're called standard candles, because we know their luminosity. And the specific kind of unique methodology I use for my project is called cosmography. So typically when you do cosmology, you fit to models such as lambda CDM, which is what I have been referring to as the standard model. Um, so what you'll do essentially is you'll take your data, you have this pre-existing model, which is this mathematical function, and you'll vary the parameters because they're different like unknowns you can vary until the curve you get kind of fits your data. The issue here is that while this might be kind of useful for figuring out like the parameters themselves, which are cosmological values such as the Hubble constant or equations that determine the nature of dark energy, if you're assuming an underlying model and you're fitting to that, you're not actually getting any information about what the actual like model is, right? Because you could be using a completely wrong model, but you're just tweaking the numbers until they seem right. And especially in this, new era where we're not sure if the model we've been accepting for, decades is the correct model, this is not as ideal of an approach anymore. So what I use is an approach called cosmography. So this is a method of calculating parameters by using Taylor polynomials. So literally like equations like, like ax squared plus bx plus c, if that's a second degree equation, to model expansion. You can choose how many kind of degrees of freedom you want. And so you're literally using mathematical functions to map the expansion instead of assuming, a cosmological model. And I already discussed Y redshift. So just to recap, the problems are the Hubble tension, the fact that there's a massive disagreement between the Hubble constant, which is how fast the universe is currently expanding when you use different methods, and the fact that there are cracks in lambda CDM, which is the currently accepted model in cosmology. So my objective is to not get an exact value for the Hubble constant, but instead I'm going to calculate the evolution of the Hubble parameter. So the Hubble parameter is the Hubble constant, but not specifically right now. So it's how fast the universe is expanding at any given time. So the Hubble parameter measured at our current time is just the Hubble constant, basically. And I want to use cosmography to determine when deviations from lambda CDM occur. So essentially, I'll be using cosmography, getting expansion rates at different redshifts, so different times in the history of the universe. I'll compare that against to what the model predicts would be the expansion rate at all these different times to see when, again, issues are actually occurring. So maybe other people can build on, they know where to focus when they're trying to resolve this problem, essentially. So I used Python, I used the standard libraries, and I took the supernova data. So the y-axis here is essentially the distance from us, roughly, and the x-axis is redshift, or again, so as you go to the right, this is further in the history of the universe, and I sorted them into small bins. So I analyzed the data separately. You can see they're different colors for each bin based off of redshift. So for example, I used a redshift range of 0.024. So every 0.024 in redshift I analyzed separately. I'll get into more into that why later. And I fitted a line to each bin of data using chi-square minimization. So I used linear cosmography. And again, going back here, the reason why I had a max redshift range is because if you're fitting, let's say you're fitting lines to a curve, right? I don't know if you guys are taking calculus or anything. When you're fitting slopes, tangents to a curve, they're only good approximations for small changes in redshift, right? If I tried to fit one tangent line to the entire curve, it'd be wildly off. That's why I determined a maximum range using some like calculations that the error from using a linear approximation would not be that great. So essentially, again, I'm taking slopes to a curve to get the expansion rates. So I took the slope of each of these lines from each of the different bins and transformed it into the Hubble parameter. So for each of these bins, I essentially determined how fast the universe is expanding at what that time it was. And then I graphed it across time and compared to lambda CDM. These are the equations I used. You can just derive these from standard cosmological equations. So this pink line is what lambda CDM predicts. Again, this is the expansion rate on the y-axis versus redshift, or how far it is in the history of the universe. And what you can see, it'll become more clear as I go on to the next graph, is that one conclusion is that for high redshifts, the error blows up. So again, these dots are what I got for the expansion rate, and these are the error bars. So I can't really infer much for high redshifts. But what you'll see is really interesting for low redshifts is that first, what I calculate is that the expansion is slower than the model says it is. Then there's kind of this oscillation where it rebounds up, right? Here, it goes back down. So there's this kind of low redshift oscillation with regard to the expansion rate versus what the model predicts. And this is the same graph, but essentially instead, I'm taking how many sigmas or error bars away it is from the mean. So this zero line is basically the pink line, right? And I'm seeing how many of these error bars it is away from the pink line. You see, so this is roughly 2 error bars away. So it corresponds to this. And it becomes way more clear that there is this low redshift oscillation that begins at roughly a y redshift of 0.25. This is corresponding to 3.7 billion years ago in the history of our universe. And this is really important because, again, one, it's a further hint that lambda CDM is flawed. You can see for low redshifts, again, this is not a good, doesn't really fit well with my calculations. And it supports alternative dark energy models that predict oscillations relative to lambda CDM. So there's a lot of these. I'll just talk about one. It's called causal back reaction. So what this says is that the universe isn't actually accelerating, but instead gravitational lensing. So as light passes through matter, because the matter isn't distributed evenly, essentially, this causes us to perceive an acceleration even when there isn't one. So supports any model that predicts these oscillations, my measurements. And finally, in regards to the Hubble tension, which is the crisis I'm looking to solve, the fact that there's an upward trend again for lower redshifts. So what I find is faster than what the model finds could be a reason why that when we take these late universe measurements, again, close to our time versus the early universe measurements, the Hubble constant is higher because if lambda CDM is flawed, then all these measurements from before are kind of null and void. And that could be the reason why there is this tension in the first place. So in terms of limitations of future research, the data I showed you earlier was only using statistical error. So statistical error is like Gaussian error. It's basically just the fact that, you can't get exact measurements. Um, I didn't include systematic error yet, which is basically the fact that when these telescopes might function differently on any given day, like it's more sensitive, it's less sensitive, and scientists actually take this into account. This is a little outdated. I actually did include systematics in my most recent update, and I'll tell you that nothing changed really, like there wasn't a big deviation, so my results mostly stood. Um, the biggest limitation is the fact that you'll recall that the dark energy survey, it only provided around 1600 supernovae, and it was for high redshifts, right? So for low redshifts, like around here, they didn't use their own data. They took from other data sets basically and they stitched it together. They had to match the systematic error and other stuff. And when I find interesting results, again, in this low redshift range, this is roughly where they took like their data and matched it with the old data. And maybe the reason why there's interesting results isn't because there's actually interesting stuff, but the fact that they might have combined the data sets incorrectly. That's a possibility. But they did like publish their own paper saying we did this correctly, basically, and they showed the methodology. So it's not that big of a limitation. For future research, I kind of chose the binning size, so how like wide or thick these bins were. Each line I fitted to manually, which is not ideal because like if I change the binning size, I get different results. So I'm not sure like if human bias could have affected this. So I do want to incorporate machine learning to find the optimal binning size. If I can kind of like vary the binning size and use machine learning to see where there's the least variation as I change it. Essentially, that's like kind of the sweet spot probably, and I can use machine learning in the future to find that. Also, if I incorporate extra data sets, what I can do is I can actually get a measurement for the Hubble constant. Because again, I'm only getting stuff relative to a model right now. I'm getting not getting like definite numbers, but if I add extra data in, I can actually get a measurement for how fast the universe is currently expanding. So thank you for listening. Do you guys have any questions?
Yes. Okay, Aidan, thank you so much for your amazing presentation. We enjoyed it a lot. And yes, we do have some questions in the chat. So let's move on to the Q&A part. So I have a question actually. So how did you determine the optimal Y redshift binning range of 0.024? And was there a specific reason for that choice?
Yeah, so I mentioned it was again the fact that when you have a curve, right? Because the model is a curve, it's not linear, but I'm using linear approximations. I'm taking like tangents to the curve. I wish I could draw it out, but these lines are not going to be good approximations to the curve for a high like variation in x-axis range. So I have to use a small, again, change in input. And I determined this exact value of 0.024 because if you do the math, this is where like a linear approximation hits 1% error. So I determined like 1% is the maximum amount of error I would allow before like the bins became too big. Because the problem with having small bins, right, is that if you have like two supernovae in one bin, then the error kind of dominates. You can't get any good results because the data is like too thin. You want like good, high quality, dense data. But again, if you make the bins too large, then the line isn't a good approximation of the curve anymore. So this is kind of the sweet spot I found by using this 1% error budget. That was my limit, basically. I wouldn't let it get bigger than 1%.
Okay, thank you. Our next question is, how do your results specifically challenge the lambda CDM model?
So again, I think it's clear in this graph. If you look here, again, like for this, you can see there's no good correlation. It's kind of just all over the place. This is when I'd say you see a clear trend again at around 3.7 billion years ago. Um, if everything agreed with lambda CDM, all these blue dots will be again on the zero line here. That means complete agreement. They're not, especially for these dots, especially they're like 2 sigma away. If you remember from like math and stuff, two standard deviations away is kind of like that means something's wrong basically. And again, for lower redshifts, I'm saying that lambda CDM here, for example, it's too slow. The universe is expanding faster than what lambda CDM says. And for here, for these redshift ranges, the universe is expanding slower than what lambda CDM predicts, basically. So my expansion rates don't agree for low redshifts.
Okay. What are some good resources, books, for example, books, websites, YouTube channels, or courses you would recommend to someone who's curious about astronomy or
So,
physics?
Mhm. um, I think it's important that you get general knowledge, and you don't have to go straight into like, the weeds, like the technical stuff. I would say you should become interested first. Do some like fun educational stuff. There's this good channel. I don't know how to, it's hard to spell out. It's called Kurzgesagt in a nutshell. Just search up like in a nutshell. They have amazing animations for these astronomy stuff. Um, and for books, and also sorry for YouTube channels, if you want to go into more technical stuff, there's this woman called Sabine Hossenfelder. She's like German. She does really good breakdowns of like modern science news, especially in like physics and astronomy. She's very good. And if you're interested in my subject area, which is cosmology, and you want to get more technical, if you search up cosmology talks, they kind of they like bring in authors of papers and they get them to do a presentation and have conversations with them. That's very technical, but also very helpful as someone who like because not everyone wants to read all these like dense research papers um or at least just like jump into them straight. I found it helpful to like watch the videos of the authors talking about the research before reading the research itself. It made it a lot more clear. For books, you can if you're a beginner and you don't know calculus, you should get Sham's Outlines for Astronomy. That's basic stuff. And there's this website called usaao.guide, which is also good. But if you want to get into more deep stuff with harder math, and you should have a physics background before using these books, you should use an Introduction to Modern Astrophysics or Fundamental Astronomy. Those two books are very good.
Okay, perfect. Thank you so much.
Yeah.
We have a question in the chat from Hemi. So, have you heard of the new Wallerent telescope coming out?
I actually have not, but I really love that you brought up telescopes because at ISAO, Flora and I and all these other people, what we've been doing is we have this initiative called the Telescope Initiative, where we kind of raise money from local businesses, grants, other things, and we actually donate them to community centers and stuff. Because I personally believe that if you're not into all this theoretical stuff, because not everyone is, who doesn't like looking at the night sky, right? Everyone likes that. So we want to bring that wonder to other people. So if you want to donate or work with us, or if you know any local businesses or organizations that you think would be willing to donate money, please contact us and let us know, and you can be a part of our telescope initiative, which I think is really special.
Thank you for bringing that up, Aidan.
Yep.
All right. I have a question actually. Do students need a strong background in programming or math before starting research in physics or astronomy?
Yeah.
And how did
Oh
you
yeah. Finish the question. Yeah.
and how did you build up those skills over time?
So I'd say programming and math, 100% yes. You can't sometimes when you run into issues, like you can't just, you have to have a base knowledge of, programming, math, whatever. You can't just rely on outside sources. I just learned how to code at a pretty young age. And once you know how to code in one language, it's not very hard to transfer those skills to other languages. Like I learned Java, but it's not hard to transfer to Python. Math, yes. If you're really serious, you should probably learn some stuff outside of what you learned in school. But even just math and programming themselves aren't really enough, I would say. You need a background in physics and preferably whatever field of astrophysics you're like kind of doing. And me personally, like I'd say there's not many good resources online for high schoolers, or they're very hard to find. Like what I told you earlier about all the resources, like in books and channels and websites, I had to like find myself. But what I think is really good is that here at ISAO, we actually compile all this for you on the website. And we have guides and articles on how you can get into the research yourself. So definitely check that out. Or if you think you can contribute to that and you have something special to offer, also contact us. That would be great. We'd love to have you, work with us.
Yes, thank you, Aidan. And also our website is isao.com, www.isao.com. Also follow our Instagram at
It's not isaoleague.com or
no, it's just isao.com for
oh,
yeah, but for Instagram it's at isaoleague.
great.
Yes, I'll type that in the chat later. Okay. So our next question is, what's your biggest piece of advice for staying motivated when research gets frustrating or when the results don't really turn the way you expected?
So, I would say again, like there will always be a time where research the results don't come out as expected or something goes wrong. Like I said, again, like right now I have an issue. Like right now, if I press run on my code, it's gonna give me like 10,000 error messages, right? So I'm current like the process of being a scientist is obviously, working through all these mistakes. Definitely just take a step back, breathe, and don't like, just if you're frustrated, what you want to do sometimes you bang your head against the wall, just keep trying to run your code or fix the mistake head on. And just that won't get you anywhere. That won't like get you anywhere. Sometimes you need to just like press undo a lot of times. You need to like redo whole sections and just like as long as you have a general understanding of like what your end goal is and if you have again like what I talked about earlier, you should be interested in your field, right? That should be like an intrinsic motivation for you. So again, just choose your topic wildly and choose your topic wisely so that you actually like want to do the research even when there are setbacks and um just take a step back when you have to and just breathe.
Yeah. Okay. Thank you. Next question. You mentioned watching Cosmos as a child. Are there any like specific moments or plot that really stuck with you or inspired this specific research?
So I remember when I was a kid, what stuck with me most was that I've always found that art and animations and like the visual stuff is most appealing, especially to children. Like I was like 5 years old, whatever. When I saw the supernovae, like the dead stars exploding, and I remember the narrator, like Neil deGrasse Tyson, he had such a good way with words where he described like stars as, living objects. They would fight a war against gravity and they'd die and they'd explode, right? And I saw these animations of the supernova explosions. They were really beautiful. And they weren't real, right? They were animations, but as a kid, like I didn't know that. I thought they were like real pictures of supernovae. And that obviously was like really cool to me. What's really cool is that, 10 years later, when I'm doing this research, I actually am using supernovae myself. Again, dead star explosions. Those luminosities, how bright they are, is how I can get these results, right? And like that wasn't like on purpose. That kind of just a coincidence, but that's a really good, nice like connection. I think that was really wholesome. But that's why I think when you do outreach and stuff, it's really important that you highlight the cool part of astrophysics because it's like easier to get lost in math and stuff, but there's really amazing stuff happening out there in the universe that we, as humans, we can't really even imagine, right? All these massive explosions, these galaxies, these distances between galaxies, they're like, we can't even comprehend them. So it's important to, be able to put images to that, I guess.
True, I agree.
Mhm.
Next question is, what was the most surprising thing you discovered during your project? Like some, for example, something that you didn't expect.
So like I mentioned earlier, the dark energy survey, the data set I used, it mostly got high redshift stuff, right? Sorry. Above 0.33. So if I go the graph here, it's like here, right? So this is the data Des got essentially. But if you'll remember, my results that were interesting are like here, right? So I didn't get interesting results from the new data. I actually got interesting results from the old data that they personally, like, again, stitched together. And I didn't expect this, right? I didn't expect low redshift regions to be the areas of interest. Um, and what I might do with this in the future is that I didn't put this in my future research, but there are older supernovae compilations with a lot more data in these ranges, and I might redo my analysis there and see what results I get. Because again, like so what I found out what happened that was unexpected was that I got interesting results in the regions where there wasn't new data actually.
Mhm.
And that kind of just shows, you never know what to expect. And it's again like these unexpected things that happen, that's what provides, the most interesting and impactful results essentially. Like the fact that I found something that I didn't expect in the beginning, that like informs my future research essentially. So yeah.
Okay, thank you.
Mhm.
We have a question from our chat audio. So for visual learners, are there any webpage or tools you would recommend to visualize these phenomenons hands-on?
That's a really good question. I personally don't know any actual like tools. When I talk about visual, I usually like mean like content. So I'm sure there are like actual websites where you can make the stuff yourself, but for me personally, like it was just watching like either TV shows or YouTube videos that would kind of that's what helped me visually. But I personally don't because I know there definitely probably do exist like supernova simulators or stuff like that. So I look into that. But for me personally, the visual aspect was from consuming like content created by other people. But definitely, I'll look into that more. It's very interesting. That's a good idea.
Okay, thank you. Thank you for the question and the response.
Yeah.
Another question from Hemi. So, Hemi is interested in your thoughts on the recent U.S. brimstone opening of the sky. So, what are your thoughts on that?
So I'm not sure what you mean by opening of the sky. I mean, the closest thing I can think of to is that um, what's interesting about my field of research is that there's new data coming out every year, and there is this new like telescope program. It's called like Opening the Sky or something, I think, something like that. And they have like 4,000 supernovae lined up because cosmology, again, it's practice of data analysis. Like I don't get data myself. Even like PhD cosmologists, they're relying on the telescope people, right? So every year there's new data coming out, and there's this new survey again, which I think is called Opening the Sky, and they're gonna have a lot more data at all redshifts. And again, I would redo my analysis with that data and see what would happen there. So that's definitely something I would do in my future research, but I'm not sure what you mean specifically by that event.
Okay.
Yeah.
Let's see. So, one last question.
hmm
What's your dream future research topic in astrophysics? Do you want to continue
yeah.
on
Uh-huh.
MSDM, for example, or maybe discover like a new research topic you wanted to do? Can you elaborate?
I would definitely want to do something related to the Hubble constant because this is the biggest, again, unsolved problem in cosmology and probably just like general physics and astrophysics. This is like one of the biggest unsolved problems. Um, like they're literally like scientists like who have beef over this stuff, like different groups of people. They actually argue over this, which I think is really interesting because you typically don't think of like scientists as, these emotionally charged people, but they get like riled up about this stuff. So I definitely want to do stuff in cosmology and the Hubble tension. Maybe not in because again, like I mentioned, it's not just supernovae. So maybe I would do something with the CMB instead, which is the other method I haven't touched. Or, there's other types of data like baryonic acoustic oscillations and all this other stuff. So I would probably want to do something related to the Hubble tension, but not with the specific type of data I'm using right now, basically. That would be my dream research. But I would still want to go into this like topic. I think it's very interesting.
Thank you, Aidan.
Yeah.
That's the end of our Q&A part. Is there anything else you want to talk about or elaborate?
Yeah, thanks for having me 100%. I think just if you found this interesting, check out our website. And if you think that you have anything to offer in terms of, because we do a lot of stuff, we do the Telescope Initiative, we have other webinars if you're interested, like this one, you should check out other upcoming stuff. We do just general STEM education and outreach to other schools, and we have guides on our website. If you think you would either, find use in that or you want to help us make it, contact us or go on the website. Yeah, thanks for having me.
Aidan, thank you again for your
Yep.
amazing presentation and also answering our questions.
Yep.
Thank you all for joining us today. I hope to see you all on our next webinar.
Yeah, follow our Instagram too. Follow our Instagram.
Yes.
Thank
Thank you.
you.